come back this particular discussion. So now what we have discussed is the renewable energy, types of renewable energy, national status, some of the worldwide status, and all these things. So now what we are planning is that we'll discuss now slowly go towards discussion of the wind energy in more detail. So when we go in detailed discussion of the wind energy, one of the fundamental thing that is required or the knowledge that one should have, again, the fluid mechanics. Because when you talk about, as I've been talking about this, that mostly what we are going to look at the aerodynamics perspective of this wind energy. Obviously, later stage we will touch upon some of these design related constraint and things like that. But primarily, the discussion would be confined in the context of the aerodynamics and all these things. So obviously, to do that, the fundamental things for doing such things is the fluid mechanics. So what we would go about it will have our this fluid mechanics that will do some review, and then we'll move to the aerodynamics, so that one will have some knowledge about basic fluid mechanics, and then we can easily discuss about fluid mechanics and things like that. Okay. So first point which comes is what is fluid. So you can see this nice picture here where some of these water drops which are falling in a pool of water. So water is definitely fluid. So unlike other things, fluid is also made of discrete molecules. And obviously, whatever we'll do in this particular course, it would be treated as continuum. So we are going to consider everything under continuum hypothesis. That means nothing is going to violate this continuum hypothesis as of now. So that means uh, when you talk about that, which means if you look at the continuum approximation, so small fluid volume, sometimes we call it a fluid particle, contains many atoms per molecule. So that means these fluid particles are going to contain small atoms per molecule. So that's one of the continuum approximation. Obviously, alternative way one can think about it's a length scale is very larger than the molecular length scale. Obviously, that brings to some kind of a number, the Knudsen number that defines the thing. Obviously, these continuum scales are preferred choice for any kind of engineering applications because most of the applications we are dealing with are in nature in continuum. So that's what. Now, the first thing when you talk about fluid mechanics, obviously one has to, I mean, one can go through the textbook of the fluid mechanics to review their knowledge and all these things. What here we are planning to do, we are going to touch upon the basics of fluid mechanics, and then we would move to the aerodynamics of the wind turbines and things like that. So the point here is that different subtopics that we would kind of discuss here or touch upon. some detailed discussion or information, if someone is needed, then you are always requested to refer to the text. Now, coming back to that, the first thing that we'll talk about the fluid statics. So again, the question comes back is that what is fluid? The fluid, the material that flows or rather deforms continuously under shear stress. So here is a picture which you can see. This could be solid or fluid. This could be solid or fluid. This is fluid only because this continuously deforms. So from this picture, when there is a force which is applied in the top surface, you can see the deformation that takes place in these two pictures. So fluid is something which continuously deforms under shear stress. So which other way one can say that under static condition fluid sustains only normal stress. Okay. While solid sustains to deform shear stress, fluid flows under shear. So zero shear prevails in static fluid. If this is kind of a free surface, this is the liquid, and this is the force diagram which is going to happen. Okay. So this is obviously connected with the solid because solid would deform to some loading, but it will try to sustain the shear. Whereas fluid try to flows. Okay. Now, if we carry forward the same logic or the same statement here, the we can derive the equation for fluid statics. So this is an infinitesimal fluid element here. Obviously, these are the coordinate directions, so x and z. Then this direction normal pressure Px, this is Pz, and weight of the element which is calculated. This is this hypotenuse normal pressure at the angle. So we can do force balance. So x direction force balance, z direction force balance, and obviously both the directions we can do the force balances, and we can get this sin theta cos theta. So essentially, what we get is that Px equals to Pz minus half rho Gz. And if the infinitesimal fluid element delta Z goes to 0, then these are all same. So pressure at a particular point is independent of direction. So that becomes independent of scalar. So this was already kind of achieved by this famous experiment, which is known as Pascal's barrel buster experiment. So it was conducted in 1646. So where, I mean, obviously you can see this picture which is available in the internet. Then you can see how somebody is getting in the top and you have this. So this is a nice experiment where we get to know about the pressure and all these things, but this is a famous experiment in the fluid mechanics. Now, coming back to this particular fluid element and having this force distribution, so the static equilibrium of this fluid element, what we can say that if you write down the forces and you can identify all these forces are surface force, whereas this is the body force, which is coming from the this component. So when you talk about the fluid element in static equilibrium, okay, then the surface forces and the body forces collectively or the sum of that has to be 0. So obviously one can have an understanding that as the size of the fluid element reduces, the body force drops faster than the surface force. That's how the connectivity between the surface force and the body force, that one can figure that out. But this is what happens when the fluid elements are kind of in equilibrium. Okay. Now from here, one can derive the equation for the fluid statics. So we taken this kind of a small cuboid, then we write down the pressure on different surfaces. Obviously, you can write this pressure using simple Taylor series expansion. Okay, and then neglect the higher order term, so you could establish that thing. So what we can do, let's say if I try to write net surface force in the y direction, that means this is the direction we are talking about. Okay, then we write the net surface force in term of pressure. This is coming from this, then this, so which will get me minus LP by del y. Now, if I consider all three directional forces, then this is what I get, the surface force in all three directions. Okay. Then collectively I'll have that. Now the second thing comes as the body force. So which is weight of the fluid element. So this is straightforward. So which will be rho g v. I mean, obviously the word kind of an one can think about mg actually. Okay. Now the total force on that particular fluid element would be the surface force and body force. So this is what it is. Now if the static fluid element, the total force is 0, so this goes to 0. So what I get is that del P is rho g bar. So obviously this concept can be extended for the rigid body motion as well, but we'll not go in discussion of that. I mean, those who are interested, they can see through the textbooks and all these things, that how that thing can be achieved. Okay. Now, coming to the fluid part, second is that, so we have got that basic equilibrium of the fluid statics. We can talk about kinematics, so which will describe the fluid motion. So how to describe the fluid motion? Okay. So there are two ways one can describe. One is the Lagrangian, other is the Eulerian. So which is again material or total derivative or the partial derivative. So all this would come into the picture. So now first let's look at the Lagrangian derivative part or description part. So here what we do that, here we our primary attention is fixed to a particular mass of fluid as it flows. So what we try to do, this is an example of a billiard boards where we try to look at this each of these individual balls and their motion. That means we fix each of these particle and try to track them. So that means you track their position vector, velocity vector of each fluid particle. Obviously, any fixed mass system as a function of time. So you try to locate their positions, velocity, location. So essentially, the individual fluid particles are always tracked in this Lagrangian description. While we talk about the Eulerian description, we focus on some control volume, which could be imaginary, usually fixed in space, and then fluid flows in and out of the control volume. For example, this is the control volume. This whole thing is the control volume. And the surface which are doing that, that is called control surface. And here the fluid goes in, it goes out. So usually in the Eulerian concept, we do not track each particle. Instead, we rely on the field variable. That means something coming in, going out. Obviously, Lagrangian description helps in deriving the equation. Eulerian frame is more often used for the solution. So here we have a fixed control volume, and then you allow the flows of the fluids to flow in and flow out of the system. Now we can have Eulerian representation. So here the important flow variables are the velocity vector, pressure. Okay, so they are the essentially they are function of space, time, and so that. When you have fluid particles which usually contains large number of molecules at a particular points, it attains the value of the field variables assigned at that point. Okay. Now the flow field can be set steady if the time derivative to be zero and steady otherwise. Tangent fields evolve into steady and periodic state and all these things. Dimensionality, which is primarily dependent on the spatial coordinate system, so which could be 3 because we are having those kind of dimensions. So here is an example in terms of looking at the Lagrangian description. Here the fluid particle passes. So these are the different point or the different time where this particle is tracked, and we try to track the particle speed. That means at different time instance, so it's a single individual particle when it is passes through these points. So at different time instant, their velocity has been tracked. Is this is a steady or unsteady flow? Now, if I look at the Eulerian description, that means the flow comes here, flow goes down. So at different time instant, A and B, they would show same amount of velocity because it's a fluid which comes in and goes down. So these are the differences. So now you can interpret physically what is del by dt, dv by dt. So dv by dt is also written capital dv by dt. So how do we relate this rate of change of B of a fluid particle located at a particular point for a given time instant to the rate of change of B to the point space? So this is where you get the total derivative, which is also same thing. One can write dv by dt is having a component called partial derivative and then the convective derivative. So when you talk about the flow to be steady, then this partial derivative has to be zero for all flow variable. Then you can say that that is steady. I mean, one can find out this expression. I mean, simply by using, so dv by dt is essentially I can write in terms of limit. So at a particular, I mean, if we have a t and x, then we can have t plus delta t and x plus delta t minus this. So we segregate these things by doing little bit of algebra. So this gets you del v by del t, and this is u del v by del x, assuming del x. So similar way, one can extend that to three-dimensional space. In general, one can write. Okay. So that's how you connect your total derivative with your partial derivative and the convective derivative. So that's the connectivity of that. So again, we can look at this particular example. Here you can see there is a cold fluid coming in, goes through some pipe here, and then finally goes out as a hot fluid. So the temperature what is coming in, and when it passes through these different channels, it's higher than. So this is a steady state operation of the cold heater. So fluid gets heated up inside the heater. So del T by del T of any fluid particle is zero, but dt by dt is not zero because there is a total change. So convective derivative of T is not zero. Now here is an example where fluid comes in, you have a profile like that, then it goes through the contraction, so it increases, then again so it is So it is again steady state, uniform flow in convergent divergent nozzle. So it first accelerates and then decelerates because there is a change in area. So du by dt of a fluid particle is zero, but du by dt is not zero. Again, the convective derivative part is not zero. So that gives you an example. So similarly, you can see this particular example where the flow goes through pipe. Obviously, pipe has this constant area, then diverging area. So here it's in one-dimensional flow, then it becomes two-dimensional here. Finally, it becomes a bit independent of what you can see here. So your 3D flow field shown by cigarette smoke. Okay. So this particular picture, you can see when it comes out, then how this structure looks like. Obviously, it's quite complicated and important structure, but say. So now, given a flow field, one can or should be able to visualize the or retrieve the velocity acceleration of the flow field. So if you have a given a flow field like this, then the acceleration of the particle is given by this. So here the pink arrow shows the acceleration vector, magnitude and direction at each point. Black lines show the streamlines. The figure shows velocity and acceleration field simultaneously. So one can calculate this. Obviously, as soon as we say that, the question which brings in or comes up is that what is streamline? Streamline is an imaginary line in the flow field. The tangent at any point of the flow field indicates the velocity direction. That means if this is my streamline, then the tangent here that would indicate the flow field. So if I have a two-dimensional velocity field, so that will have two components. Then in the streamline segment, that would be dr. This will have two segments. The dr is parallel to v. Then I can get dx by u equals to. So that is the equation of streamline. And if I use it in 3D, then this is how it is. Okay. So that's purely, I mean, one hand we are trying to define the basic fluid behavior, but at the same time, one can think about we are primarily doing some kind of an vector calculus to find out this thing. Now, streamlines are imaginary lines in the flow field which are tangent any point indicates the velocity direction. So you see these streamlines and the tangent shows the velocity direction. But one important thing, two streamlines must not cut each other. They never cut each other because these are given by these particular equations where the velocity is okay. So again, fluid particle cannot cross the streamline because the streamlines cannot intersect. And when you have a series of streamlines and all these things, then it can make sense steam tube, which are made of streamline. So if any fluid particles enters here inside the steam tube, it remains within the steam tube. It cannot go out of the steam tube because the fluid particle cannot cross streamline. This is the important thing. And the steam tube is made up of streamlines only. So for example, we can look at, this is the given a velocity field. So you can find out the equation of the streamline. So you can use this simple equation dx by u and then do the integration. So this is what you get. So obviously, as you change the value of C, you will get different family of streamlines and things like that. Okay. Now we have streak line, which is locus of fluid particle that have passed sequentially through a prescribed point. So stick line is one can look at this kind of dye visualization and to get this. So it's a individual fluid particle. You try to find out the locus of that. So if you take a fluid particle, it comes here, it passes through this point. So that locus is going to give you the stick line. That means it's individual streamline that goes to. And then you have another terminology or definition is called the path line. So that is the actual path traveled by any individual fluid particle over a prescribed period of time. So if the fluid particle at the starting here, then go like this in middle and then finally end there. So this is the path line of the fluid particle. You can see this wave in a free surface flow. The path lines are captured along exclusive protocol. So we have to summarize what we have. We have streamline, we have streak line, we have path line, we have timeline. So streamline is imaginary line in the flow field where tangent at any point of that gives the velocity direction. Streak line is the locus of the fluid particle that pass sequentially through a prescribed. Path line is the actual path of the fluid particle which has traversed or which have traveled over a which has traveled over a period of time. And timeline is a adjacent fluid particles that were marked at the same instant of time. So essentially, you get all these definitions which are important to now what we talk now, we talk about some kind of an system which is called the control mass system or closed system, or we talk about control volume or open system. So what you say the system is essentially the collection of matter with fixed identity. It doesn't change mass with surroundings. Then you have control volume, which is again a geometric entity. It could be fixed or moving, rigid or deformable in space with where fluid may flow. Then the control surface. So if you look at this is your control volume. So this is a boundary which is called control surface. This is the moving boundary of this. So you can have this kind of system. So what is important here is that we can apply the conservation of mass to a particular system. So this particular system, you see, this is a kind of a system boundary and this is the control volume. So how do you use the above equation to find equation of mass conservation in control volume? So you can define a control volume like this. From point 1, fluid comes in, point 3 goes out, point. So we can say that the change in the mass in the control volume would be the whatever mass is coming in and whatever mass is going out. So that's how is essentially the change in the mass. That's what you try to find it out. So obviously when you try to do that, the another important things one has to define is the extensive versus intensive property. This is the mass, B is the intensity, small beta is the intensity, B is extent. So in general, the intensive and extensive property is only thing to find out that what is dependent on mass and what is independent on mass. So that is what we talk about these different properties. So now what we're going to look at is we're going to look at these equations, how one can define or derive from the control volume system. But we'll stop the discussion here and take the discussion further from here. Okay.